In this video, we're going to connect the dot product that we just saw with the idea of constructing a plane in 3 dimensions. If we imagine drawing some plane, we can define that plane, in particular its orientation, by building a vector that is perpendicular to that plane. We typically define that as a normal vector or a perpendicular vector, and we usually use n for normal. And the idea is that this entire plane is somehow perpendicular to that vector. Well, how do we capture that? We have a reference point, which is what we call P naught, and we know its 3 coordinates, x naught, y naught, and z naught. And what we can then do is imagine what defines all the points in the plane. We'll pick any point elsewhere, call it x, y, and z. If we connect the point we know to that point on the plane, and we know that those are supposed to be perpendicular, then we can define our plane using a dot product. What we have is that our n vector dotted with any vector in the plane has to equal 0, and we can then create the elements of that. The vector here is the n point, x minus p naught, which is x naught, y minus y naught, and z minus z naught. That is our vector here. Let's call that u. That's u is usually for unit vectors. We'll call that v. If that dot product equals 0, we can then expand that out, and let's use the values a, b, and c here for the components of the normal vector. What that is going to give us is a times x minus x naught plus b times y minus y naught and plus the third component, the c, z minus z naught. That has to equal 0, and that is the equation of a plane. You'll notice it doesn't have any complicated factors in it. We just have a constant times x, a constant times y, and a constant times z. With our intuition from first term, that should feel like the extension of what we had with a straight line, only now what we're getting has one more variable, and so we get a plane instead. We can apply this formula for a simple example where we're provided with the idea of a plane that we're looking for and a vector that is normal to that plane. And that normal vector has been given to us. It's the vector 2, 3, and 4. And we've also been provided with a point on the plane, and that's our p, which is 2, 4, negative 1. And then what we can imagine is any vector that we care to draw in this plane, connecting it to an arbitrary point x, y, z, what's going to make this point a valid point on the plane is that if we take a dot product of this vector in red and this vector in green, we must get 0. Well, let's build that out. We have the vector 2, 3, 4, and if we dot that with square brackets, this vector here, well, that vector is this point minus that point. So it's the vector of x minus 2, comma y minus 4, comma z minus minus 1, so z plus 1. And that dot product would have to equal 0. All right, we can then expand this out. We get 2x minus 2's, 3y minus 4's, and 4z plus 1's equals 0. That's a perfectly fine place to stop if you like. Some people like expanding these out though. We have 2x plus 3y plus 4z's, and then we can lump the constants together. We have a negative 4, a minus 12, and a plus 4. So 2x plus 3y, clean that up a bit, plus 4z's, and the 4's cancel, so we end up with just minus 12 equals 0. So either form, that one or that one, would be completely valid representations of the plane shown in blue here.